Welcome everyone to the Spectral Geometry in the Clouds seminar. Today we have the immense pleasure of having Jürgen Jost from the Max Planck Institute, and he will speak about spectra of graphs and hypergraphs. The floor is yours. Thank you.
Yeah, thank you very much for giving me the opportunity to speak here. As I already said, it's quite convenient to be able to do that over the internet, because until a few minutes ago, I participated in a conference in Singapore, and now I'm happy to talk to you. Here's the abstract that you have already seen. So I will speak about the spectral theory of the Laplace operator on graphs. And my own background is in Riemannian geometry. And so I see the analogies with the spectral theory of Riemannian manifolds. For instance, we have Chiga type inequalities, but there are also some different phenomena. I will not only speak about graphs, I will also speak about hypergraphs, where the first problem to overcome was to come up with an adequate definition of a Laplace operator that can also offer such analogies. But then there will also be other aspects. After all, graphs and hypergraphs are discrete objects. And so we will look at discrete combinatorial problems, but the Lovasz extension allows us to translate some of these discrete problems into continuous ones. So my talk will have two parts. The first part will be more of an elementary nature. The second part will be more advanced. If you have questions for either part, please do not hesitate to interrupt me, just as you would in a physical talk. But most importantly, I will report about joint work that I'm doing, that I did with Rafaela Mulas on one hand and Dung Zhang on the other hand. So Rafaela is a former PhD student of mine, but she now has her own research group on the spectral theory of hypergraphs. And Dung Zhang is a postdoc who is an expert on Lovasz extensions. He was a student of Kung-Ching Zhang in Beijing. And we have various papers in journals and on the archive. I will not give you detailed bibliography because you can easily check that yourself, but I should advertise that the three of us are currently writing a book together. But then, as I said, all the results that I'm going to state without other attributions are joint work with one or both of them. So let's first look at some principles. So we have a finite and connected graph with n vertices. And for simplicity, I assume that the graph is simple, that it doesn't have multiple edges between vertices and it doesn't have self-loops. These restrictions are not essential. Vertices that are connected by an edge are called neighbors. And there's an abbreviated notation shown on that slide for this. And the degree of a vertex counts the number of its neighbors. So in the diagram below, the degree of every vertex is indicated. It goes from 1 up to 4 in this particular case, or 1 up to 5, I'm sorry. So there are some principles there which are important from an abstract perspective, but they will guide our thinking. If you have a function defined on the vertex set, V is the vertex set of the graph, and if you have two neighbors, then we can look when we can compare the values at these neighbors, and we can look at the difference, which are called d of f. The df of I and j being neighbors, is f of I minus f of j. Some relation is satisfied, namely df of ij plus df of jk plus df of ki is equal to 0 when we have a triangle in the graph. So this is not symmetric in I and j. After all, the f of I and j is a difference between f of I and f of j. We have a sign there. And so therefore we should also consider, instead of simple edges, oriented edges, which I indicate by the brackets here. So this oriented edge ij goes from I to j, and we should then look at edge functions which are antisymmetric. So gamma of the edge from j to I is equal to minus gamma applied to the edge from I to j. And then we can also look at some accumulation over edges. So we define operator d star. The star will be explained in a moment. D star applied to an edge function that can then be evaluated at the vertex I, essentially counts what goes out of the edge minus what comes in at the edge. And for normalization purposes, we divide by 2 times the degree of I. Again, that will be justified in a moment. But the essential principle of the accumulation is here that we look at what comes in and we look at what goes out and consider the difference. So we can then compose these two operators. After all, d is applied to a vertex function and gives an edge function, and d star is applied to an edge function and gives a vertex function. So we can look at the two compositions, d star d, which then would be applied to a vertex function, and d star, which would be applied to an edge function. And they have the following form. I call them graph Laplacians. So delta 0 on vertex functions is f of I minus the average of the value of f at the neighbors of I. And delta 1 of an edge function gamma looks at the flow through that particular edge. What comes in at one end, at the head, at the tail, and what goes out at the head. And we compute the difference there. So we have these two operators that will play an important role. I will study them and try to extend them later. There's one important remark here. If you're a graph theorist, then you should be aware that delta 0 is not the graph Laplacian that is considered traditionally, for example, in books on graph theory. The so-called algebraic graph Laplacian multiplies the value at every vertex with the degree of that vertex. And unless all the vertices have the same degree, in which case the two operators are simply multiples of each other, the properties, and in particular the spectra of the operators, can be quite different. I will be mainly interested in the spectrum of the operator delta 0. So for instance, A is a combinatorial operator, so it reflects, for instance, how many paths you have between two vertices. Whereas delta 0 is some kind of a diffusion operator, so it reflects the probabilities of random walks. I will come to that in a moment. But from a geometric perspective, the operator delta 0 is actually more natural. Now, let me try to explain the star. We have a scalar product for functions from the vertices, which I define as a product of the values multiplied by the degree. And we also have a scalar product on oriented edges, where I just multiply the values at the edges, and of course I take the sum in the first case over all vertices, and in the second case over all edges. And then the two operators are adjoint. the operators d and d star are adjoint. So df comma gamma evaluated with the edge scalar product is equal to the product of f and d star gamma evaluated via the vertex scalar product. And then you compute that the two operators are self-adjoint and non-negative. So there's an obvious and easy corollary. Since the operators are the same, except for interchanging the two factors in the product, they have the same non-zero spectrum. The multiplicity of the eigenvalue 0 can be different, but the other eigenvalues are the same. And the eigenvalues are real because the operators are self-adjoint, and they are non-negative because the operators are non-negative. So let's look at delta 0. It's sometimes simply abbreviated by delta. As I already said, it compares the value at the vertex with the average of the values at its neighbors. And in fact, it can be seen as a generator of the natural random walk on a graph, where from one vertex, if you are at step at time n at particular vertex, then at time n plus 1, you can be at any of the neighbors of that vertex with equal probability. And therefore, it satisfies some conservation law because the total probability is equal to 1. And in fact, it also satisfies the maximum principle. As you know from the Laplace operator in real analysis, or the Laplace operator, Laplace-Beltrami operator on Riemannian manifolds. If we look at Laplace G equal to 0, then because of the maximum principle or by an easy computation, the only solutions are the constants. I assume that the graph is connected. Yeah. Otherwise, you could have different constants on the different components. And for any other eigenfunction, for an eigenvalue lambda not equal to 0, you have the orthogonality with the eigenfunction for the eigenvalue 0. And since the constant function 1 is an eigenfunction for the eigenvalue 0, f is orthogonal to 1, which means that the sum over all I of the degree of I times f of I is equal to 0. So some kind of average of f is equal to 0. As I said, I'm interested in the eigenvalues. So here's the eigenvalue equation. And we can, of course, reformulate it just in terms of the values. So 1 minus lambda k of uk of I is 1 over the degree of I times the sum over all neighbors of uk of j. As I already mentioned, the first eigenvalue is 0, and since the graph is connected, that is a simple eigenvalue, and therefore the others are positive. And if we have n vertices and we have n degrees of freedom, so there are n eigenvalues altogether if we count them with multiplicity. Now, what do the eigenvalues tell us? So the second eigenvalue, lambda 2, is positive, and it tells us how difficult it is to cut the graph into two large pieces with few connections between them. I'll return to that in a moment. This was already discovered many years ago by Dodjuk and by Allon and Millman. The largest eigenvalue is at most 2, and it is equal to 2 precisely if the graph is bipartite. Bipartite means that we have two classes of vertices without any internal connections inside the class. So vertex in one class can only be connected to vertices in the other class. And then 2 minus lambda n tells us how different the graph is from a bipartite one. That was done together with my graduate student Frank Bauer and independently by the computer scientist Trevisan. There's one other very simple observation that I made with another graduate student, Anirban Banerjee, namely the eigenvalue lambda equal to 1 indicates no duplications. So if lambda is equal to 1, then we have this relation that for every vertex, the average of the values of its neighbors is equal to 0. And then you can very easily construct an eigenfunction, namely take the vertex f that we duplicate, that is indicated in the diagram. So f is a vertex at the lower right corner. I don't know whether it's easy to see. I can enlarge the picture a little so that it becomes clearer. So we have the vertex f, and then we duplicate it to vertex f prime, where duplication means that f prime has the same neighbors as f. And then we can easily construct an eigenfunction, namely we just put u of f equal to 1, u of f prime equal to -1, and we put u equal to 0 everywhere else. Then obviously the eigenvalue equation is satisfied. The averages for all neighbors vanish, and we have constructed an eigenfunction for the eigenvalue 1, which then shows us that there is some difference from the situation in Riemannian geometry, because here we have a very localized eigenfunction, which you would not find on a Riemannian manifold. And it turns, in fact, out that empirically that is quite useful. If we look at empirical networks, define the Laplace operator there, look at the spectrum, then if we find high multiplicity of the eigenvalue 1, then we can speculate that the network has been generated by repeated no duplications.
I'm sorry, I have a quick question here.
Please.
So this tells us that if we have a node that's duplicated, then we have an eigenvalue 1. But
yeah.
Does this always go the other way around? When you have eigenvalue 1,
No.
you will be able to find the structure?
No.
Mm-hmm.
In fact, if you take a pentagon
Mm-hmm.
and a triangle and connect them at a single vertex,
yep.
Yeah, then you can also find an eigenvalue 1, which doesn't come from a no duplication, because that graph is not obtained from a simpler one by no duplication. So this is a very good question, yeah. But so the answer is no, and so therefore, as I said, when you look at an empirical graph, you find a high multiplicity of the eigenvalue 1 that gives you an indication, but not a proof that that graph has been generated by repeated no duplications.
Thanks.
But in fact, we have, just as a side remark, we have studied the spectrum of many graphs, of many empirical networks systematically. And of course, there are many regularities there, and looking at the spectrum can tell you a lot about the graph. Anyway, so let's come back to this result of Dodchuk and Alon Milman. And I should also mention Fan Chung here, because she was the first mathematician who studied this normalized graph Laplacian that I'm studying here systematically. So there's a constant in graph theory, which is called the Chiga constant. It was first, in fact, introduced many years earlier, perhaps almost half a century earlier, by Polya in graph theory. But the point is, it is called the Chiga constant because it is analogous to the Chiga constant in Riemannian geometry, which provides an estimate, or which can be estimated by the first non-zero eigenvalue. Now, that was the fundamental discovery of Chiga in Riemannian geometry, and then Dodchuk and Alon Milman found out that something that an analogous result also holds in graph theory. Even though graph theory, of course, is much easier than Riemannian geometry, and you don't have to deal with the analytical difficulties and so on. But in this relation was first discovered in Riemannian geometry. So here's a constant, h. So we have a graph, and we have a subset S of the vertex set, and we denote its complement by S bar. And then we look at the number of edges between S and S bar. So we split the graph, the vertex set of the graphs, into two components. We want to do it in such a way that there are only very few edges between these two components. But on the other hand, we also want that the volumes, that is the sum of the degrees of the vertices in a component, are not too small. And h then is obtained by minimizing that over all S that are non-empty and do not coincide with the entire vertex set, but is otherwise completely free. And so we look at that minimum there. So we want to cut the graph into two large vertex sets with few connections between them. That is, we want to cluster the vertex set, as one also says in graph theory. Then there's a fundamental estimate that this quantity is controlled from above and from below by the first non-zero eigenvalue, which according to my notation is lambda 2. So that already tells us that the spectrum encodes important geometric information. Computing the spectrum is not so difficult numerically. Computing H, which is a combinatorial optimization problem, is pretty hard. In fact, most of these graph theoretical problems are NP hard. And so the estimate, of course, need not be sharp, but nevertheless, lambda 2 gives us good bounds. And so it tells us then also something about the geometric significance of lambda 2. Namely, if you look at the eigenfunction, then you have two nodal domains, and these two nodal domains then would correspond to an approximation of the best S and the corresponding S bar. Now, look at the dual Chiga constant that was defined by my student Frank Bauer and myself, and in a different context, as I mentioned, by Trevisan. So then we partition the graph into three sets. The important ones are V1 and V2. We look at the number of edges between them and divide by the sum of their volumes. And this constant is always less or equal to 1 if you maximize over all partitions, and it is equal to 1 precisely if the graph is bipartite. Namely, when we have the two classes of vertices, then the edges between them contain all the edges in the graph, and so then the number of edges is equal to the sum of the volumes. And then we showed that there's an analogous estimate for the largest eigenvalue and H bar. So the largest eigenvalue also has an important geometric interpretation. Now we can rewrite things. I will come to that a little later. But instead of minimizing over subsets of the vertex set, we can also minimize our functions. We look at functions from x from the vertex set to the real numbers, and then look, instead of the edges, we look at the differences, xi minus xj, and instead of the volume, we look at the values normalized in an optimal way, and then according to our scalar product, we have to multiply again with the degree. I will come to the reason why that is so in a moment in the less elementary part of my talk. But first I want to introduce another quantity, namely I just take the maximum of the inverses of the degrees of two vertices connected by an edge. And then together with Raffaella, we showed that this also can control the largest eigenvalue. It controls the largest eigenvalue from below, and it controls the largest eigenvalue from above by some multiple. And one can rewrite it. Maybe the details are not so important here. Just the point is that this gives us the control of the largest eigenvalue in terms of a rather simple quantity. And of course, since I already told you that the largest eigenvalue is related to the bipartiteness of the graph, or to how different it is from being bipartite, it is natural that Q is also related to bipartiteness. In fact, it can be rewritten as a maximum over all subgraphs that are bipartite. And then I look at the ratio of the degrees in that subgraph, which typically is smaller, divided by the degree in the original graph. And then I normalize by the number of edges in that subgraph. So now, as already said, the computation of the spectrum is relatively easy. There is a MATLAB routine, for example, where you can easily do it for graphs with up to 500,000 nodes, and with some more effort, you can even handle larger graphs. Whereas the combinatorial problems in graph theory are typically hard and p-hard, and so therefore it is not surprising that the spectrum does not completely determine the graphs. They are so-called isospectral graphs, that is, graphs that are not isomorphic but have the same spectrum. Let me try to draw you one. It is already mentioned here. So we look at a complete bipartite graph. So let's just take two classes with two vertices each. So this is one class that is connected to every vertex in the other class. And so this is the graph K22. And then I do it differently. Split up things differently. So I look at what is also called a star graph, which is the graph K1, 3. And already these two simple graphs have the same spectra. Namely, they have the eigenvalues. They have the eigenvalue 0, as every graph does. They have the eigenvalue 2 because they are bipartite. And all the other eigenvalues are 1 because both graphs can be obtained by repeated node duplications. You just start with a single edge and then duplicate one or the other vertex of that edge once or twice, and then you obtain that graph. And so, in fact, this also shows you that often you can determine the spectrum of the graph without really having to compute it, just by some simple principles. So, but although the spectrum does not completely determine the graph, it reveals important qualitative properties, and I've given you some examples already in the beginning on the previous slides. We can extend that to weighted graphs, which is not very difficult, as long at least as long as the weights are non-negative. You can extend it to directed graphs when the operators are no longer self-adjoint, and you may in general encounter complex eigenvalues. That was systematically studied by Frank Bauer, my student in his thesis. But I want to go into a different extension. Namely, I want to look at hypergraphs. So in a graph with vertex set V and edge set E, each edge connects just two vertices. In a hypergraph, however, a hyperedge H can connect any number of vertices. And so then the question is how we then get the signs that were important for the definition of our Laplace operators. Well, the inspiration comes from chemical reaction networks, And in fact, one of our projects is to systematically study the hypergraph consisting of all chemical reactions ever reported in the literature, connecting all chemical substances ever reported in the chemical literature. So by now we know more than 40 million reactions and more than 20 million substances. And we want to study that gigantic space with the help of these combinatorial algebraic tools that we are developing here. But that also then gives us some suggestion of how to define the operators. As we know, the chemical reaction transforms a set of ingredients into a set of products. They need not be disjoint because catalysts are both. And there are some ways to model that. We could either consider it as a bipartite graph, where one set of vertices would correspond to reactions, the other one would correspond to the substances. Or we could model it as a hypergraph, where reactions are hyperedges that connect sets of vertices. And in fact, I want to do the latter. Now, chemical reactions are directed. They go from ingredients to products, and they are typically not reversible. And this would, of course, make spectral analysis more complicated, as I had already indicated before. Namely, you would then get complex eigenvalues. However, there's a mathematical trick which we did. We look at so-called oriented hypergraphs, and we work with signs as in cohomology theory. That was done with Rafaela Mulas as part of her thesis. There's some interpretation here which might be helpful. Instead of letting hyperedges contain sets of vertices, we look at it the other way around. We consider hypervertices, which are collections of vertices that are connected by an edge. So either you could look at it this way here. There's a hyperedge connecting these vertices. Or you could look at it that way. Here's one vertex set. Here's another vertex set, and they are connected by an edge. And then, of course, we have such hypervertices and edges between them. We can then orient these edges, and we are back in business, as we shall see in a moment. So in what we define as a chemical hypergraph, each edge connects two hypervertices. Hypervertex is a set of vertices. And when we want to look at the contributions of a hypervertex, when we compute Laplace type operators, we simply add the contributions of the vertices contained in such a hypervertex. Or we could look at alternatively at vertices connected by oriented hyperedges with a tail and a head set. And the vertices in the tail then contribute with the opposite sign as those in the head. These are thus different perspectives. Mathematically, I will not make a difference between them. Now, then how to define the Laplace operator for such hypergraphs? Well, we just go through the steps of the construction of the Laplace operator for ordinary graphs. We give weight 1 to the hyperedges, and then each vertex gets weight, or also called its degree, which is just the number of hyperedges it is contained in. Then we define corresponding scalar products based on the weights, and we define the boundary operator for functions on the vertex set. And then with the scalar products, we find the co-boundary operator, or D star. And then we can define our Laplace operators as the two different compositions of the two operators that we have. So that makes this formal. Scalar product for functions on oriented hyperedges and vertices are essentially the same as before. Now for the boundary operator, which are now called delta, for function on the vertex set, delta f is a function on hyperedges. And so now we add up all the inputs to the hyperedge and subtract all the outputs of the hyperedge. And for the adjoint operator, we do the same as before. We just look at what flows into an hyperedge from other hyperedges and subtract what flows out of the hyperedge to other hyperedges. And again, we normalize it at the vertex that we are looking at. Then we have formulas for our two operators. They look a little complicated now, but don't bother too much. It is the same as before, same principle as before. Thus notation gets more complicated. And for graphs, we recover the operators that we had introduced before. So it's really a generalization of what we have done before. Now again, delta 0 and delta 1 have the same non-zero eigenvalues. And the multiplicities of the eigenvalue 0, of course, they are different, but they just count the number of vertices minus the difference of the multiplicities is equal to the number of vertices minus the number of hyperedges. Because after all, on the vertex set, we have as many degrees of freedom as we have vertices. And on the hyperedge set, we have as many degrees as we have hyperedges. And since the other eigenvalues are the same, the difference between the multiplicities of the eigenvalue 0 is exactly that difference. You could also see that as some version of the Euler principle. Now there can be vertices that are both in the tail and in the head of a hyperedge. They always cause an eigenvalue 0 for the Laplace operator on vertices. More interestingly, closed systems of reactions, they cause an eigenvalue 0 for the Laplace operator on hyperedges. In the same way as closed loops on the graph cause an eigenvalue 0 for the Laplacian on edges. And again, bipartiteness causes large eigenvalues. How large it can be depends on the degrees of the hyperedges. Just as a side remark, the theory of Laplace operators can not only be extended from graphs to hypergraphs, can also be extended to simplicial complexes. That was started by Benno Eckmann already in 1944 and studied in more detail in the PhD thesis of my student Daniela Horak. And both hypergraphs and Riemannian manifolds, of course, carry geometric or metric structures. And it has been an important and somewhat ironic research direction in recent years to extend concepts that were originally developed in Riemannian geometry to more general metric spaces, in particular to graphs, hypergraphs, simplicial complexes, and so on. And these principles of Riemannian geometry, of course, were developed by Bernhard Riemann. And if you want to read about that, you can look at the English version of his habilitation address, which I have edited a couple of years ago. And so therefore it is natural to look what these have to say for hypergraphs. I should mention that not only the spectra of Laplace operators show strong analogies, also the concept of curvature, which is even more fundamental to Riemannian geometry, can be extended to general metric space, in particular to graphs and hypergraphs, in fact, in different ways. We can extend sectional curvature and we can extend Ricci curvature. But that is not my topic today. Now, I want to get a little more, now it gets a little more difficult. I start with an abstract principle, that of a Rayleigh quotient, where I have an n-dimensional vector space, a finite dimensional Hilbert space with a positive definite scalar product. And I have a self-adjoint linear operator like my Laplace operators. And then I can look at the so-called Rayleigh quotient, which simply is the product of the operator applied to G with G, normalized by the product of G with itself. Now, if you look at critical points of that quotient, then we see by a simple computation, by the quotient rule, that this then becomes an eigenvector of the operator G, and the eigenvalue is precisely the value of that Rayleigh quotient. So the eigenvalue equation can be obtained by looking at critical points of this Rayleigh quotient, which again still is pretty simple. And conversely, every eigenvector is a critical point for the Rayleigh quotient. Then we have the famous Courant Fisher-Weil min-max principle. We look at the family of all k-dimensional subspaces. And then in each subspace, we maximize this quotient. In each subspace of dimension k, we maximize this quotient, and then we take the minimum over all subspaces, and that gives us a case eigenvalue. We can also turn things around. We can minimize over subspaces and then take the inside subspace and then take the maximum over all subspaces, and again we get the eigenvalues. And the subspace equation, of course, can also be obtained in terms of scalar products with the previously found eigenfunctions. And so we get this characterization of the eigenvalues, and in particular, we can obtain the smallest eigenvalue as a minimum of the Rayleigh quotient and the largest eigenvalue as a maximum of the Rayleigh quotient. Now, we want to come back to this Polya-Chiga constant, we recall it. And we also recall the second eigenvalue now that can then be obtained according to the Rayleigh principle as a minimum over all functions that are orthogonal to the eigenfunctions for the eigenvalue 0, that is the constants. That is now that condition below the min. And then we look at the Rayleigh quotient. And we had this relation, just stated earlier, that lambda 2 and h control each other. Now, if you look at it, then you see something surprising, namely h is obtained by a discrete operation, combinatorial operation, whereas lambda 2 is obtained by a continuous optimization because we are looking at functions. So how could such two quantities control each other? Well, there's a beautiful method, the so-called Lovasz extension, which I now briefly recall. We have a finite set that is in our applications our vertex set, we have its power set, and we look at functions defined on the power set. For normalization, we usually assume that f of the empty set is 0. Now, any subset of V, that is any non-empty member of the power set, can be obtained with its indicator function in R to the V, which just is equal to 1 on those vectors of the unit cube, on those corners of the unit cube whose indices are all contained in A, and it is 0 everywhere else. That is, now we have a function defined on the corners of the unit cube. It's 0 or 1 there in our case. Or then we have a function, then we can extend the domain of f to the entire Euclidean space, or if we want to be more restrictive, to the interior of the unit cube by this formula here. That is, we have a function that originally takes values just on the corners of the unit cube, and we extend it to the function everywhere on the entire Euclidean space according to this rule. I will not so much explain this definition, but just state some basic properties. Our set function is called submodular if f of a plus f of b is always bigger or equal than f of the union plus f of the intersection of these two sets. And the fundamental theorem of Lovasz says such a set function is submodular if and only if its Lovasz extension is convex. That, of course, is very nice, because then many discrete optimization problems, namely those concerning submodular functions, are turned into convex optimization problems, which are typically quite easy to handle. And also, if we want to minimize things for submodular function, then the minimum over all sets is equal to the minimum of the Lovasz extension restricted to the unit cube. So submodular optimization by Lovasz extension becomes convex programming. And that is a principle that we also want to apply. So here are some examples of Lovasz extensions. We have set functions defined on the subsets of the vertex set of a graph. Most of them had been known before. And so particularly the Chiga constant then can be translated into a continuous optimization problem, as shown below. Now, this is an L1. There's another surprising aspect. While we have bridged the gap between discrete and continuous by Lovasz extension, there's another gap. Namely, the Chiga constant is an L1 quantity. Just take norms, whereas L2 is lambda 2 is an L2 quantity, because there, when we evaluate the scalar products, we take squares of norms. So the question is, how could such quantities be related to each other? Now, we have quotients of two functions in the definition of the Chiga constant, and then we look at the corresponding quotients of the Lovasz extensions. Now, again, we want to find critical points. So in the smooth case, X is critical for this quotient. The same principle as before, if the gradient of FL is equal to a vector, which happens to be that quotient itself, times the gradient of GL. Now, however, things are not really smooth. After all, we are looking at L1 norms, that is absolute values. These are not smooth functions. And then there are different ways of how to approach that. We can look at eigenvectors and eigenvalues just by generalizing this equation, now taking nabla as a subgradient and take the minus sign. For the minus sign, use the Minkowski sum of convex sets, and then we can extend that. We can also directly look at critical points and critical values of the gradient of the subgradient of the quotient. Or we can look at minimax values, as was suggested by the Rayleigh quotients. So we can look at mth order minimax values and define them as our eigenvalues. In the smooth case, as in the theory of Rayleigh quotient, the results are the same. Whatever we do, we get the same eigenvalues. But in the non-smooth case, in general, we have only subset relation, namely every eigenvalue that is obtained by some minimax scheme as a critical value of the quotient becomes a critical value in the sense that the subgradient that 0 is contained in the subgradient of the quotient, and every such very critical point or critical value is contained in the eigenvalues as defined by number 1. And the reason is that G may have zeros. That creates problems. Now we want to relate L1 and L2. So we, instead of taking squares, we take piece powers. Maybe since time is going fast, I will not go through all the details. So instead of using the Rayleigh quotients with squares, I take them with piece powers. And then I get the corresponding eigenvalue problem number 22. We have this operator, it's now a nonlinear operator, and we get a nonlinear eigenvalue equation. For p equal to 2, of course, it is linear, but for other values of p, it is nonlinear. And we want to let p go to 1 in order to interpolate between the L2 and the L1 aspect. And we can do that in the general context of Lovasz extension. So we can define a Chiga-like or Chiga-type constant for any function pair satisfying certain conditions, similarly as before. And for a simple graph, of course, we can do it as before to obtain our Chiga constants that we started with by a suitable choice of functions. But now the point is we can imitate the scheme for other functions. And for a chemical hypergraph, we can also define a corresponding quantity. Again, we try to cut it up into different pieces, but again, time is moving on, and I just leave it at that without explaining all the formulas here. And we have our Lovasz extensions, which are quite natural, as we see in the bottom. Now we look at piece powers of differences or piece powers of values. And then for the second eigenvalue of this delta p, we have the corresponding quotient. And again, we can try to optimize that. And for p bigger than 1, in fact, this is again natural eigenvalue problem that also works for hypergraphs, but going with p to 1 becomes difficult because then we have absolute values, and the derivative of an absolute value becomes undetermined at 0. And that causes many problems, which I will not go through in detail, but the point is we can obtain also inequalities for h, our Chiga constant, and the second eigenvalue, the first non-zero eigenvalue of these p Laplacians that are similar as before. And if we formally let p go to 1, then h becomes the eigenvalue lambda 2 of the 1 Laplacian. One can make that rigorous for graphs. That was already done by Kung-Ching Chang and by Matthias Hein and Setzer. But the question then is how to, we can extend it to hypergraphs, and we can now more deeply understand that limit here. Now comes something written very small, because otherwise it would not fit onto the slide. Again, maybe we don't go through all the details. I just mentioned that the point is that the derivative of the absolute value becomes undetermined at 0. It jumps from -1 to 1. And so there's this interval from -1 to 1 in which anything can happen, and we have to allow for that possibility. in the definition of our operator, which in a certain sense is the derivative of that absolute value. So that is a formal definition. As I said, I will not really go through the details. We can even do it on a hypergraph. Again, I will not go through the details. And then we have an eigenvalue problem. Now, again, where things can become undetermined between -1 and 1. And we have to solve the corresponding equation. And now things become more difficult. There may be more eigenvalues than you would expect from the number of vertices. And in particular, therefore, not all eigenvalues arise as minimax values, but nevertheless, the proceeding gives you an intuition or an explanation why the Chiga inequality holds. Namely, lambda 2 was for the ordinary Laplacian was an L2 quantity, H is an L1 quantity, and you can essentially interpolate them with the help of Hölder type inequalities. So that is the reason. And if you do it with P and let P go from 2 to 1, then in the limit you get an exact equality, which gives you a geometric interpretation or an analytic interpretation of the Chiga constant or geometric interpretation of the lowest eigenvalue of the one Laplacian. Okay, with that, I should stop here because my time is almost over and I should leave some time for questions. Hopefully, motivation, the beginning was clear and some of the more difficult stuff could also be explained, at least at some general level. So thank you very much for your attention.
Thank you very much for the talk. Do we have any question now for the speaker?
I have a question. It's Alex. Perhaps a very naive question. Does the machinery that you develop have analogy in the Riemannian setting, in the continuous setting?
Yes, I mean essentially it all came from that continuous setting. Yeah, so the Chiga inequality was first derived in the continuous setting. There the question was to find on a Riemannian manifold to find a hypersurface which has low volume, a small volume or area depending on the dimension, which cuts the Riemannian manifold into two large pieces.
Yes, but I mean with the different, when you go to hypergraphs instead of graphs and so on, is there something corresponding to this in the Riemannian setting?
Well, I mean, graphs, and one should probably say that graphs and hypergraphs are kind of belong to the same class of objects, which as such should be compared to Riemannian manifolds. So the distinction between graphs and hypergraphs doesn't seem to have any analog in Riemannian geometry. Okay, thank you. In one sense, one could think of simplicial complexes as analogs of Riemannian manifolds, and then a graph or even hypergraph would just be a one-dimensional object, which of course is trivial in Riemannian geometry, but which, as we see here, is not so trivial in graph theory and combinatorics.
Thank you, Alexandre. Do we have any other question?
So did I understand it correctly that for P going to 1, the Rayleigh quotient becomes non-smooth?
Yes.
And
well, I mean, it's already slightly non-smooth for P smaller than 2. Yeah, the derivative can become infinite. Yeah, but for P equal to 1, really it degenerates very, very badly.
But it is continuous still, right? It's Lipschitz.
It is Lipschitz, but the derivative jumps. Yeah, I mean, just look at the function absolute value of x to the p. Right. Yeah, and let p go to 1, then you see how it becomes singular, and that is reflected here. And now there's this jump of the derivative at 0, And so that leaves a region that is kind of undetermined if you look at this eigenvalue or optimization problem. So everything can happen between 0 and 1. If the value is the value of x is 0, then anything can happen for the derivative.
So can you then define eigenvalues and eigenfunctions as critical points in the sense of Clark's subdifferential or something like this?
Yeah, and that is what I try to do. I mean, there are different ways of defining them. Yeah, and you can just look at critical points of that ratio. We can write down the eigenvalue equation, yeah, which you formally would get if you apply the quotient rule, or you can look at those procedures that you have in geometry and the calculus of variations to find unstable critical points, namely by minimax schemes. But in general, all these can give you different results. Yeah, that is a problem here. And in fact, we have an example of a hypergraph where really the different procedures gives you different numbers of eigenvalues.
Okay. Yeah, thank you.
Please, I have just a small question.
Yes, go on.
Yes, thank you very much, Professor Jost, for your talk. And I am a metric or metric hypergraph.
Sorry, I couldn't hear the question. You were muted in between. Please repeat it.
I am asking on we can speak about Laplacian operator on metric hypergraph.
On what? On what graph?
On metric hypergraph. Metric hypergraph.
Yes, yes. I mean, the Laplace operator can be defined in quite some generality. What essentially you need is to have some scheme of counting of defining differences, yeah, in and out, yeah, and you need scalar products.
So we can define it as the case of Laplacian operation on metric graph. There is
yes.
And about the Kirchhoff condition vertices, it will be the same, or we must to adjust on the Kirchhoff condition.
Yeah, well, the Kirchhoff condition was for electrical networks, and it is a algebraic graph Laplacian that I mentioned briefly in the beginning. You can, of course, do it there. The difference is very simple. In my scalar product, I counted every vertex with its degree. If you just count every vertex as 1, yeah, then you would get the algebraic graph Laplacian as it occurs, for example, in Kirchhoff's theory of electrical circuits.
Thank you.
You can also put whatever weights you want on the vertices and on the edges and define corresponding scalar products. And then again, you get corresponding Laplacian. And the theory is essentially the same.
It's almost the same, we can say.
Yeah, it's all essentially the same.
Yes.
As long as you don't have directed edges.
Okay.
Yeah, if you can go from I to J, but you cannot go backwards. Yeah, then it becomes more difficult because then you no longer have these scalar products and you no longer have self-adjoint operators.
And about the four domain, it's the same. Or the four domain of the Laplacian operator. I mean, the quadratic form.
Yeah, well, I mean, since you mentioned forms, the analogy is between the Hodge Laplacian and differential forms in Riemannian geometry. Yeah, and the corresponding operators either on graphs or hypergraphs, which just corresponds to 0 and 1 forms, or the corresponding operators on simplicial complexes. And simplicial complexes, you have high-dimensional operators, which are analogues of the Hodge Laplacians on higher order differential forms. You can develop a completely analogous theory there.
Yes, okay. Thank you very much, Professor Jost.
Thank you.
I have a
go on.
Okay. Yeah. Can I just ask a question? You mentioned your motivation from the chemical reactions. So what kind of information do you want to get about this from your theory?
Well, I want to get some insight into the structure of the space. So how many closed systems of reactions you have, how uniformly chemical space is covered. Yeah. Also, to what extent the progress of chemistry, because this data in fact are time resolved. So we have this data for every year since the early 19th century. So for about 200 years, we have this data, so we know which substances and reactions were known at the end of each year. And so then we are doing also historical study. We want to see to what extent the qualitative properties of that exponentially growing space remain the same. Yeah, we have already figured out that there's an exponential growth, stable exponential growth over 2 centuries with about the same rate, but we can distinguish 3 periods in terms of their variance. Yeah, one going until around 1860, the other one going around 1980. With relatively sharp transitions in the qualitative features of the growth. Yeah, but then we want to, of course, do more refined studies there and explore the spectral properties and all the other properties. We also look at so-called graph curvatures, so Ricci curvatures of graphs, and we evaluate those, and that already tells us something about the structure of chemical space. That is an ongoing project.
Okay, very interesting.
Thank you for the question. Do we have any other questions for the speaker today? Well, thank you all for being here, and thank you again, Professor Jost, for the talk today.
It was my pleasure, yeah.
Yeah, thank you. And we will reconvene next week at the same time as usual. There will be a talk by Nalini Anantaraman. We'll talk about quantum ergodicity for expanding quantum graphs in the regime of spectral delocalization.